Hello everyone. So welcome to the experiment number 1 NMR and IR lab. In this lab we will give you some brief introduction about the NMR spectra analysis, how you interpret the proton NMR and carbon NMR, what are the terminologies are involved, and then deep and theory you will study from your lab manual or some other videos. So let's start from nuclear magnetic resonance spectroscopy. So we'll start from here.
We will be going over the nuclear magnetic resonance NMR spectra interpretation. First, we have the 1H NMR or Proton NMR, which analyzes the chemical shift using the delta ppm scale, which ranges from 0 to 10 on the x-axis, and on the y-axis we can measure peak intensity. Similarly, using the C13 NMR or carbon NMR, we can analyze the chemical shift using the delta ppm scale, which ranges from 0 to 200, and on the y-axis we have the peak intensity. One of the main differences between the 1H NMR and 13C NMR is the range from 0 to 200 in the C13 and 0 to 10 in the 1H NMR. In the 1H NMR, as we move from 0 ppm to 10 ppm, we see the protons de-shielding or moving downfield, and they have a higher frequency as well as a higher chemical shift. As we move from 10 ppm to 0 ppm, the protons are shielded and are moving upfield with a lower frequency and a low chemical shift. Similarly, in the C13 NMR, as we move from 0 to 200, the carbons are being de-shielded and moving downfield, and they have a higher frequency as well as a high chemical shift. As we move from 200 to 0 ppm, the carbons are shielded and moving upfield, and they have a lower frequency and a lower chemical shift. From 0 to 100, we see that this is the aliphatic region, and we can see molecules like cyclohexane. And from 100 to 200, we have the aromatic region, and we can see compounds with rings in their structures. Similarly, in the 1H NMR, from 0 to 5, we have the aliphatic region for compounds such as cyclohexane, and from 5 to 10, we have the aromatic regions for aromatic compounds with rings. We will now be going over relevant terminology for the NMR spectrum. First, we have multiplicity, otherwise known as spin-spin splitting, and this follows the n+1 rule. So here we see a singlet characterized by the single peak, which stands for one signal, and is represented by a lowercase s. Similarly, we have doublet represented by lowercase d, which represents two signals or two peaks. We have the triplet represented by a lowercase t, where we can see three peaks and three signals. We have a quartet, which has four signals and four peaks and is represented by a lowercase q. We have a multiplet, which is represented by a lowercase n, which represents many signals and many peaks. We can use this example to understand multiplicity and the n+1 rule. Here we have a CH3, and using the n+1 rule, this n stands for the neighboring hydrogens, so there are two of those. So 2 plus 1 equals 3. This means that this CH3 would show up on a spectra as a triplet. Over here, this CH2 has 3 neighboring hydrogens, so 3 plus 1 equals 4. This CH2 will be represented as a quartet on the NMR spectrum. Here, both of these CH3s will show up as two peaks since they have one neighboring hydrogen, so n+1, 1 plus 1 equals 2. Each of these will show up as a doublet together. This CH right here has 6 neighboring protons, and therefore 6 plus 1 equals 7. This will show up as a septet or as a multiplet on an NMR spectrum. This is a 1H NMR spectra of CH4, a molecule called methane. As we can see here, methane has 4 hydrogens, and all 4 protons or hydrogens are equivalent and give us 1 NMR signal or peak, as we can see here by this singlet. When we perform the integration of this peak, we see that we get 4, which represents the 4 hydrogens on methane. This is a 13C NMR of methane, CH4. We can observe variant field a single peak, which represents the carbon in CH4, the single carbon.
Okay, so now we will see another example of 1H NMR of ethanol. So ethanol represented by CH3, CH2OH. So here you can see these CH3, these 3 protons are equivalent. They have the same environment. They attach only this carbon. These CH2 are in the same environment. It's separate, equivalent, and this hydrogen is different. So we supposed to see 3 different peaks, 1, 2, 3, and this CH3 will appear as a triplet because of n plus 1 rule. This CH3 have 2 hydrogen neighbors, so 2 plus 1 3. So integration of this CH3 is 3 proton, representing 3 CH3, 3 protons on CH3. This peak around 3.8 have the 4 lines, 1, 2, 3, 4. And why they are 4? Because this CH2 is experiencing 3 neighboring protons. So 3 plus 1 according to n plus 1 rule, multiplicity rule. So 3 plus 1 is 4. So we'll see 4 peaks, and the integration of this peak is represent 2 hydrogen. So means the CH2 have 2 hydrogen and the CH3 have 3 hydrogen integration, and this will be CH triplet and this will be quadruplet. Now OH hydrogen, this OH hydrogen usually have appear as a singlet because it's less affected by the multiplicity, and they also come as a small peak. Usually OH, NH, they appear very small. So here you can see that we have triplet, singlet, and quadruplet. Now and they are all in aliphatic area. So because ethanol have aliphatic, so they are appearing within 0 to 5. So this is the aliphatic area. Now we'll see the carbon NMR of ethanol. So here we have 1, 2, only 2 carbons are there. So they will appear, all the carbon appear only in a single line. There is no splitting because this is called a proton decoupled NMR. So one CH3 carbon will appear as an upfield, and then CH2 carbon will appear around 60 because it is neighbor to the oxygen.
Another important term in 1H NMRs is integration, represented by this symbol, and it is basically the number of protons. Integration in NMR is the process of measuring the area under each peak, and it represents the number of hydrogens or protons.
Okay, so now we'll see another example of proton NMR using this ethoxybenzene. So in case of ethoxybenzene, here we have ethoxy group, CH2, CH3 is called ethoxy group, and this CH3 have 2 neighbor proton. So according to n plus 1 rule, this CH3 signal will come 3. So triplet, 3 proton, and this CH2 have 3 neighboring proton. So 3 plus 1, 4. So this CH2 signal will appear as a 4 line quadruplet, and integration will be 2 proton, and these 2 hydrogen have the same environment. So that is why they will appear here as a triplet, because each hydrogen have the neighboring 2 hydrogen. So 1 and 2. So 2 plus 1, 3. So triplet, and these hydrogen have almost similar environment, and they appear as here in 3 protons, but they are come as a multiplet because this hydrogen is splitting with these 2 hydrogen, this hydrogen is splitting with this hydrogen is splitting with this hydrogen, so all doublet and triplet will come together. So here is a good example of this is the aromatic region and this is the aliphatic region, right? So this is the aromatic region and this is the aliphatic region. And once we will look at the carbon NMR of ethoxybenzene, we have 1 carbon, 2 carbon and 6 carbons here, 1, 2, 3, 4, 5, 6 carbon. So this ethyl carbon will appear here, this CH2 carbon will appear here, this carbon is here, and these two have the same environment, and these two have the same environment. These two have the same environment. So these 2 and 2 will come here, 2 and 2. This is the 1 carbon, this is the 1 carbon, and this is the 1 carbon, this 1 carbon. So in carbon NMR, usually the height represent the number of carbons. So if this is the 1 carbon, you can see the height of this peak is the double. So double means it's like a just double carbon. So here we will see one line for equivalent carbons. So this was another example of and here you can see all aromatic carbon will appear after 100 and all aliphatic carbons are appearing before 100. So these were the 2 examples how to interpret the carbon NMR and proton NMR. We'll see some more examples.
The third term we will go over is the coupling constant, represented by capital J. It is measured in hertz, and it's basically the difference between 2 adjacent subpeaks in a split signal. For example, separation between doublet lines. Here we can see 2 different hydrogens which are in different environments and on adjacent carbons. The distance between the 2 peaks in the doublet is represented by J, AB. And this is the coupling constant of this doublet.
Okay, so now you can see we have seen some few examples how to interpret the proton NMR and how to interpret the carbon NMR of aliphatic compound and aromatic compound. And next video probably we will see some more examples if we have chemical formula and how to draw the proton NMR from the chemical formula and learn some more about how to interpret the NMR.